Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Deflections and Stability, and it is going to provide you a broad overview of deflections and also the elastic and plastic analysis. I am going to give you an overview of what I am covering in today's video. First of all, we will have a look at some fundamentals of the deflections, then move on to the elastic and plastic analysis of a cantilever column, then wrap up with conclusions. In the virtual walk method, the collapse load was found by considering small virtual deformations of the collapse mechanism. However, the shape of the structure before deformation of the mechanism was assumed to be the same as when there was no load on the structure. In other words, all deformation before collapse was ignored. There must be deformation before collapse. But how significant is it? It is not sufficient to ensure that the structure is strong enough to resist the applied loading with an adequate load factor against the collapse. It is also necessary to check that deflections don't become excessive. Consider the pitched portal frame shown in Figure A. The frame carries the rails for an overhead traveling crane. The crane wheels, which run on the rails, will only have a finite amount of sideways movement. Consequently, the dimension L is a critical part of the design. If it changes too much, owing to deflection of the frame, the wheels will jam and the crane will no longer be able to move. The deflections must be checked. Under normal working loads, the structure should still be elastic, so that it would be possible to find the deflections by elastic analysis. However, that is not always enough. Figure B shows a possible load deflection curve for the frame in Figure A. Although the structure would be elastic at working loads, plastic design would produce a structure with bending moments close to the plastic moment at certain critical sections. It would only need a small overload on the crane for plastic hinges to form with a large increase in the deflections. Overloading overhead traveling cranes is one of the most common problems in buildings. It is always a temptation to save time by making one lift rather two. In this situation, it is necessary to follow the load deflection characteristics of the structure. There is another potentially more serious possibility. The deflections before collapse may significantly reduce the collapse load of the structure. It is well known that deflections reduce the stiffness of struts, the so-called P-delta effect, and the same thing can happen to frames. The problem is worse in more flexible structures, where the deflections can cause an unexpected collapse mechanism, owing to overall buckling instability of the frame. Imperfections in the as-built structure can amplify the deflections. The example shows that there can be significant deflections before collapse starts. Deflections, particularly in columns with substantial compressive axial forces, can cause serious instability buckling in frames. Now we use a cantilever column to give an excellent illustration of the effect that the deflections can have on the collapse load. This figure shows a cantilever column, rigidity clamped at the base and free at the top. An eccentric vertical force is applied to the column, causing the column to bend and deflect sideways. Column properties are shown here. The values for Young's modulus and yield stress are slightly different from those commonly used nowadays, but they don't affect the conclusions from the example. The cross-section is square, side length d equal to 0.1 meter. Thus we have area moment of inertia I, elastic section modulus z, plastic section modulus s, and cross-sectional area A. Consider first the elastic behavior of the column. This figure also shows the free body diagram from cutting the column at some point x. Moment equilibrium about x gives this equation. Using the moment curvature relationship of bending moment shows here, which can be rearranged into the form where alpha squared equal to p over ei. This differential equation governs the deflections y of the column. The solution of this equation is this expression. At the top of the column, x equal to L and y equal to delta. This can be substituted into y equation to give this delta equation. Replacing alpha and substituting the column properties gives this equation. The load deflection relationship defined by this equation is shown in this figure as a graph of P against the delta. The graph is nonlinear because the analysis was second order, since the expression for the moment involved the deflection of the column. Apparently, delta becomes infinitely, and it gives PCR equal to 1.027 times 10 power 6 Newton. This is the elastic buckling load of the column. It can also be shown that when the eccentricity E is 0, the strut remains straight up to this load and then buckles sideways. A first-order analysis would ignore the extra moment from the deflection of the column so that we have this equation. This equation can be integrated twice to give this expression, where C and D are constants of integration. Using the boundary conditions of zero slope and deflection at the base, we have this equation. Substituting the values of capital E, I, and E, and putting x equal to 2 meter gives the deflection at the top of the column as delta equal to 0.12 times 10 power minus 6 p, which is a linear relation between load and deflection. This is also plotted in this figure. Now we will introduce the plastic analysis. In the column, there is a combination of axial and bending stresses. The largest stress is at the base, where the bending moment is largest. When this stress reaches the yield stress, the elastic analysis will cease to be correct. This will be shown as this equation, where the first term is the axial stress, and the second is the largest bending stress. Substituting A, Z, delta from the second-order analysis, E and sigma y gives this equation. This rather complicated equation can be solved by trial and error. This gives the load at the first yield Py equal to 0.262 times 10 power 6 Newton. It is possible, although complicated, to follow the spread of yield, but it is more useful to look now at the collapse of the column. This figure shows the collapse mechanism. The column becomes a lever rotating about a plastic hinge at the base. The reduced plastic moment, allowing for the axial force of the column, resists the rotation. At the collapse load Pc, we have this equation, and MP equal to d cubed over 4 times sigma y for a rectangular section. Putting Pc equal to n times pp, it gives MP dash expression. The moment of the collapse load Pc about the base causes the rotation of the column. This distributing moment shows here, since Pc equal to n times d squared times sigma y. At the point of collapse, the distributing and resisting moments are equal, because the column is in equilibrium. At collapse, then we have this equation. The solution of this quadratic equation gives the collapse load Pc as a proportion of pp, but the solution depends on the deflection delta at the top of the column. The collapse loads at various values of delta have been plotted in the figure of P against the delta. This figure summarizes the behavior of the column from the zero load until collapse. The broken line shows approximately the transition from elastic behavior as yield spreads through the base of the column. There are 4 points to note. The first one is that the first-order elastic line gives a reasonable approximation to the deflections before yield occurs. There is a substantial deflection before collapse occurs. A simple first-order plastic collapse calculation would have used the mechanism, but with delta equal to 0. The simple plastic collapse load, 0.59 times 10 power 6 Newton, is considerably greater than the true collapse load, about 0.326 times 10 power 6 Newton. The interaction of the second-order plastic and elastic curves, P equal to 0.364 times 10 power 6 Newton, delta equal to 0.0683 meter, is a good estimate of the actual collapse load and deflection. This is a rather extreme example because the cantilever column is very flexible, but it does illustrate the p-delta effect. In this case, the extra moments and deflections are very large, so that the actual collapse load is markedly less than the collapse load that would be predicted by simple first-order plastic analysis. The p-delta effect usually less severe than in this example, but it cannot be ignored. From conclusions what we learned, it has been concerned with deflections, axial loads, and imperfections, and the effects that they have on the collapse of structures. It was shown why it is important in some cases to know the magnitude of deflections in the structure, because limiting those deflections might be more critical than ensuring that the structure is strong enough. Any of the analysis based on the stiffness method will give the magnitude of the deflections. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,